Hello guys, today we are going to learn the interconversion among 4 types of projection formulae, that is Fischer projection, Flying-Wedge projection, Newman projection and Sawhorse projection. This is very important to learn the stereochemistry of any organic reaction. So let's go. Now we want to convert the Fischer projection formula into the Sawhorse or Newman projection formula. There is one guideline, look at here. The guideline is that the Fischer projection formula actually represents the eclipsed conformation. Look at here, there are 2 conformations of Sawhorse and Newman. This one is eclipsed, this one is staggered, and in Newman this one is eclipsed, this one is staggered. But Fischer projection formula, actually we have learned that Fischer projection formula actually 2-dimensional representation. So it actually represents the eclipsed conformation, that is, this form is represented by this one, or this form is represented by this one. Look at here, if we designate the carbon number 1, this is carbon number 2, this one is 3 and this one is 4. Now you can do in this way, say this one is 1, this one is 2, this one is 3 and this one is 4. Look at here, that is carbon number 2 and 3 are the 2 chiral carbons are there. So at carbon number 2, methyl chlorine at the right and hydrogen at the left. Methyl chlorine at the right and hydrogen at the left. And similarly, this carbon is there, chlorine at the right, hydrogen at the left, chlorine at the right, hydrogen at the left. So this is actually the eclipsed conformation which is represented by the Fischer projection. And if we just convert the eclipsed conformation by simple rotation of 180 degree, we can have the staggered conformation. And similarly, this is your carbon number 1, this is your 2, this one is 3, that is the back carbon, and this one is the 4. And this one, in this way, in the similar way, this carbon is represented by this one. So chlorine at the right, hydrogen at the left, chlorine right, hydrogen left. And the backward carbon, that is carbon number 3, the chlorine at the right and hydrogen at the left. So this conformation actually represented by the Fischer projection formula. In this way, we can convert any type of Fischer projection formula into Fischer or Newman projection formula. Now we are intent to convert the Fischer projection formula into the Flying-Wedge formula. Look at here. Let us take the molecule CHH, this is OH, hydrogen, and this is your CH3. This is the molecule of lactic acid. That is one of the enantiomer of lactic acid. Okay, if we intend to convert this molecule in this formula, which is Flying-Wedge formula, CHH. Now what will happen? How we can convert this molecule to this one? This is our guideline. If the lower part of the vertical bond of Fischer projection turns right in the Flying-Wedge formula, look at here. If the lower part of the vertical bond of Fischer projection turns right in the Flying-Wedge formula. This bond was actually vertical, but the lower part turns right. Here it is right turn. Now, say this one is CH3, so this one is CH3. Turn right, then the right horizontal bond of the Fischer formula will appear at the above the plane bond in the Flying-Wedge formula. Then the right horizontal bond, this is the OH bond, appears at the above the plane bond in Flying-Wedge formula. That is, OH will appear here and hydrogen will be here. This is the conversion. In this way, we can convert the Fischer projection formula into Flying-Wedge formula. There is one chiral carbon. If the lower part turns right, the right horizontal bond will appear at the above the plane bond, and vice versa, definitely, and vice versa. and vice versa. Look at here. If we convert, if we want to represent the molecule in this way, now what will happen? Now the lower part of the horizontal bond turns left. So the left horizontal bond will appear at the above the plane bond. So this one is OH and this one is hydrogen. If the lower part turns left, the left horizontal bond will appear at the above the plane bond. Definitely these two molecules are identical. Look at here. This is our lactic acid. This is the molecule. Here it is the presentation of this molecule. Look at here. This is your COOH, C double bond O, single bond OH. This is your OH, this is your hydrogen, and this is your CH3. So this is the presentation. And actually, if we rotate this molecule, or if we visualize this molecule from this angle, you will find this one. Again, now hydrogen at the top and OH at the bottom. This is the presentation. Definitely, these two molecules are identical. Just following this guideline, we can convert any type of Fischer projection formula into the Flying-Wedge formula. Thanks. Again, we want to convert the Fischer projection formula into Flying-Wedge projection formula. Look at here. This is our structure. This is 2,3-dibromo-butane, and this is the threoform. We know this is the threoform. In the threoform, two bromine are in the same site, and the threoform, two bromine atoms, two similar atoms are in the opposite sides, so it is threoform. We will just like to transform this Fischer projection formula into this Flying-Wedge projection formula. How can we do this? Look at here. This is the carbon number 1, this is the carbon number 2, this is 1, this is 2, and this is the 3. To go from carbon number 1 to 2 to 3, this carbon number 1 to 2 to 3, in the Fischer projection, these 3 are actually in the vertical line. So 1, 2 and 3 should be in the vertical line, 3 should be here, but to go in the Flying-Wedge projection, just this bond just rotate at the turn at the left hand. If you just observe this molecule from this angle, look at here, it should be in the vertical line, but it turns in the left. So the group at the left will appear in the frontal bond. So hydrogen will go up and bromine will go at the back side. So again, look at here, this is your carbon number 3, this is your carbon number 3. 2, 3 and 4 in the vertical line in Fischer projection, but here 2, 3 and 4 are in different lines. So this is your point of view. Look at here. If we observe the molecule from this angle, 2 to 3 to 4, it just turns right. It appears in the Fischer projection in the vertical bond in the same line 2, 3 and 4. This 2, 3 and 4 just turn right. So the group at the right, this is hydrogen, will appear in the frontal bond in the Flying-Wedge projection. So in this way, we can convert any type of Fischer projection presentation in the Flying-Wedge presentation. Our next molecule is D-glucose. We can convert the D-glucose of Fischer projection into the Flying-Wedge projection or Wedge-Dash projection. Look at here, this is your carbon number 2, this is your carbon number 2. 1, 2 and 3 are in the same vertical line. Now 1, 2 and 3, if we observe this bond from this angle, what you will find? You will find that the 1 to 2 to 3, the 2 to 3 bond actually turns left. So the group at the left side of the carbon number 2 will appear at the frontal bond, and OH obviously will go in the backward, in the back bond, in the rear bond. Okay, at the carbon number 3, look at here, 1, 2, 2, 3 to 4. This is your 2, 3 and 4. Your point of observation is from here. This is your point of observation. Look at here. From this angle, if we look this bond 2 to 3 to 4, the 3 and 4 bond just turn right. So the group appears at the right position of carbon number 3 will appear in the frontal bond. Okay, again to go from carbon number 3 to 4 to 5, 3 to 4 to 5, if we consider this carbon, this chiral carbon, your point of observation will be from here. 3 to 4 to 5, this should be in the vertical line in the Fischer projection, but here it just turn left. So the group at the left will appear in the frontal bond of Flying-Wedge position. And in the last case, here this is your carbon number 5. This 5 is here, so your point of view will be from here. If we look from here, 4, 5 and 6 was in the vertical line, but 4, 5, 6 is actually bent right, turned right. So the group at the right will appear as the frontal bond. This is the OH. OH at the frontal bond and hydrogen in the backward bond. So this is actually the Flying-Wedge projection of D-glucose. In this way, we can convert any type of Fischer projection formula can be converted into Flying-Wedge projection by following the same guideline. Okay, here we consider another aspect of Fischer projection formula, the interconversion of different Fischer projection formula. Look at here, this is the molecule amino acid alanine. It is represented in one of the Fischer projection formula. Now, how can we convert this one to another Fischer projection formula? Like, look at here, CHH. Of course, there is again another guideline. There is again another guideline. The guideline is in Fischer projection. In Fischer projection, even number of exchange among the groups attached to a chiral carbon produces the even number of exchanges, so it is produce the same isomer, same configuration. The isomer of same configuration. This is our guideline to convert one Fischer projection formula to another one. So look at here, this is your CHH. CHH remains fixed. Now if we exchange between CH3 and NH2, that is CH3 go there and NH2 come here and hydrogen is here, but there is odd number of exchange. This is not even number of exchange. Now if we inter-exchange between this hydrogen and CH3, this is hydrogen here and CH3 here. Now this configuration of this one and this chiral carbon will be identical. There are two exchanges are there, CH3 go there, NH2 come here, and CH3 go there, hydrogen come here. So there are two exchanges produces the same configuration of the same isomer. If we produce any one, if we convert say COOH here, or if we want to fix CH3 here, so exchange just any one of exchange just these two. Hydrogen will go there, COOH will come here, NH2 will go there, and if we take NH2 here and hydrogen here, it will produce the same configuration. So these three are actually same molecule. Just we verify, we just examine whether these three are identical or not. Just if we convert this one into the Flying-Wedge or Wedge-Dash configuration, this is a COOH, CH3. Look at here, CH3 turns right, so the right hand group will come at the frontal bond. This is the NH2. And if we consider this one, look at here, NH2 is here and hydrogen is here. So the group hydrogen turns right, so the group at the right, that is COOH, will come at the frontal bond. This is your CH3. Now just verify it. Look at here, this is your molecule. This is the COOH and CH3 there, NH2 at the frontal bond, hydrogen at the backward bond. So this is the actual molecule. Now if we will go here, what will happen? NH2 at the top, hydrogen here, so COOH at the frontal bond and CH3 at the backward bond. So what we have done is everything is correct. Okay, just verify it. This is the same molecule and this is the same molecule. What happens actually, this is a three-dimensional molecule and these are three different two-dimensional presentations. So to convert this one to this one, you have to apply some manipulation, some manipulated rules. These are actually the manipulated rules, but actually this molecule and this molecule are identical. Both are same molecule. This is represented in this way and this is represented in this way. This one. We can convert one Wedge-Dash formula into another one by simple just rotation of the carbon-carbon bonds. Look at here. This is our lactic acid molecule, COOH, CH3, hydrogen and OH. OH at the back carbon and hydrogen at the frontal carbon. Look at here, this is all lactic acid. This is all lactic acid. So look at here, if we like to present this molecule in this way, what will happen? Now this CH3 turn in the right, now this CH3 bent at the left. Look at here, if you just rotate this molecule, now this hydrogen will go back and this OH group will come at the frontal bond. That is, this hydrogen will be there and this OH will be there. Look at here. Of course, these two molecules are identical. This one is this one and this one is actually this one. So these two molecules are actually identical. In the same way, you can do everything. Look at here. Say this sort of presentation is there. This sort of presentation is there. Say this carbon is chiral carbon. Say again this one is chiral, this one is chiral maybe, and say this one is bromine and this one is hydrogen, this one is CH3. Look at here. So this one is present in this way. Bromine is represented by the red. Just we considered this bond. Look at here. This is your CH3, this is your carbon, bromine at the top, hydrogen at the at the backward bond. Look at here, if we rotate, just rotate the molecule in this way. Here as it was, say CH3 here, if we rotate this molecule in this way, that CH3 will come in the frontal bond on the in plane bond. Here CH3 was there. If we want to write CH3 in this way and CH3 here, now what will happen? Now CH3 is there, bromine was at the frontal bond, hydrogen at the backward bond. What will happen if you rotate CH3 at the frontal bond, then hydrogen will come at the front and bromine will go to the back. So bromine will be there and hydrogen will be there. So in this way you can convert any sort of molecule to any one. This is just about bond rotation, but in the exam there will be no molecular model, so you have to just practice these things. Just rotation, just simply rotate. By rotating the molecule, it can be converted to this one, any sort of configuration. So this is all about our different projection formula. Thank you for watching the video. Thanks a lot.